Hey guys, today we are doing our last set of notes for Chapter 6. This is 6.7, which is all about modeling with exponential and logarithmic functions. There's two major skills that we're looking at within this section. Our first one being able to classify data sets. So if I give you a set of data, whether it's given as a table or a list of points, we need to be able to identify what kind of function that is, whether it's linear, quadratic, or exponential. And then our second skill is going to be writing an equation just given two data points. So we've done a lot of different equation writing so far this chapter, but this specifically is just given 2 points that are somewhere on our exponential curve, being able to write the equation for that exponential. So that's going to be boxes 3 and 4. So let's go ahead and jump in here to box 1, which is all about classifying data sets. The first thing we have to make sure we are checking for when we are classifying our data sets is we have to make sure that our x values are evenly spaced. Make sure our x values are evenly spaced. We have to make sure there's a consistent interval, consistent gap between our different data points. If our data points are not evenly spaced, we cannot make any predictions because we don't know necessarily what the pattern looks like. If they're not evenly spaced, we can't do any of the following things. So first and foremost, make sure that there's an even space between your x values. So whether that's just increasing by 1, it could be increasing by 2, they're all even numbers, they're increasing by 5. It doesn't matter what that gap is, what the spacing is between your x values, it just has to be a consistent spacing. Once we've identified that, our different data sets are identified using a particular thing. So we know that from Algebra 1, when we're looking at linear functions, because a linear function is a constant rate of change, that all I have to do to get from one to the next is add or subtract. So what we're looking for our linear equations, our linear functions, is that what we'll call the first difference, meaning the difference between my y values, is the same. So if that first difference is the same, we know it's a linear function. So if I can just subtract my y values from one to the next, and that number that we get is the same every single time, it is a linear function. Our quadratic is taking that one step further. And again, I'll show you guys what this looks like, but for our quadratic, we want the second difference to be consistent. Our second difference is the same, meaning that the first difference going from one y value to the next y value, they might not be consistent with those first differences, but if I look at the change in those changes, it is a constant change once we get down to that second level. And that it's much easier to see once we are able to kind of put an example to it and visualize what that'll look like. Our exponential, which is what we're dealing with here, we know from throughout this chapter that in order for it to be exponential, we have to have a multiplication happening. So we have to have a common ratio, which we know looks like a multiplier. So if all of my terms to get from one to the next for my y values has a common multiplication to get from one to the next, then we know that it's an exponential function. So in box 2, we're going to go ahead and take a look at that. So again, first thing we need to make sure we're checking on is that our x values are evenly spaced. So for number 1 here, we're going from -2, -1, 0, 1, 2, 3, 4. So very obvious that that is evenly spaced. I'm just increasing by 1 for my x values, so I'm good. Now we get to focus in on the y values. And I'm trying to identify how I get from one to the next in my y values. So going from a half up to +1 could be adding a half, but then I would need to be able to add a half to get from 1 to 2. So I can see that that's not going to be the case. I'm not going to have that first difference be the same, which also tells us that our second difference is going to be different. So here, what I see, especially as we get further to the right in my data table, I can see that my numbers are 2, 4, 8, 16, 32. At least to me, hopefully to you guys, it's pretty clear to see that we're just doubling our numbers. which means we have this common multiplier of 2 to get from one to the next in my data table. So since I have a common multiplier of 2, this would be an exponential function. So we'll just write exponential there. We're all good to go. Because there's a common multiplier, a common ratio, we have that consistently between my y values. That makes it exponential. Okay. So taking a look at number 2, if we wanted to check for that first, I can see at least all of these are even numbers, so maybe there's a potential of them being exponential. But we can see that in order to go from 2 down to 0, there's not really a multiplication or a division that's going to be able to do that other than multiplying by 0. And then the rest of my data table would have to also be multiplying by 0 in order for us to be consistent. So I know that that's not going to be a multiplication. So I have to look at either that first difference or that second difference. Now, before I should have said this, I kind of do this, and when I just scan the problem, my x values here again are evenly spaced. Even though there's 2 in between each of my x values, it is still an even spacing. So it's going from -2 to 0, up to 2, up to 4, up to 6, 8, and 10. So we're increasing by 2 every single time. So, like I said, we're going to look at that first difference to see if our spaces are, our y values are evenly spaced. So going from 2 to 0, we would have to subtract 2. From 0 to 2, we would have to add 2. 2 to 8, that's adding 6. 8 to 10 to 18, we're adding 10. Let's see, 18 to 32, we are adding 14. 32 up to 50, we would have to add 18 there. So our first difference is definitely not consistent. Right? I'm not only having some negative and some positive, but they're all different numbers. So it's not linear because that first difference is not the same. But if we look at the pattern of these numbers now, going from -2 to +2, that's increasing 4. From 2 to 6, that's increasing 4. 6 up to 10, increases 4. Increases 4 to 14, increases by 4 to 18. So that level there that I just wrote in red, that is the second difference. Even though the spacing between my y values is not consistent, the spacing between those spaces is consistent. That's my second difference. So here in blue, I'll write it down here for us. Here in blue, this is our first difference. And then in red, this is that, second difference. And since this is consistent, that tells me that this is a quadratic function. Obviously, I didn't show a linear one here, but we've seen that since middle school even. We've been doing linear functions since before you guys even took a class with me. So that we don't need to really go through that. Again, it would be our first difference is the same, so you would just have an equal spacing between your y values along with your x values. So that would be what a linear looks like. So that's classifying data sets. We've been doing, again, it should be a familiar skill to us. That's the easy part of this section. The more difficult part is boxes 3 and 4. So in this, we're trying to write an equation for an exponential. We're using that just kind of that basic standard form for an exponential, y equals a times b to the x power, where a is my starting value, b is my multiplier, x and y are obviously my inputs and outputs. So if we're trying to use that equation to write the equation, that formula, whatever, to write the equation for an exponential that goes through 2 specific points, there are 3 main steps we have to do. There is a way for us to be able to figure this out. And unfortunately, or fortunately, depending on how comfortable you are with it, it does involve solving a system of equations. So what we need to do here, because we have 2 different data points, we have to plug them in to our formula. We know that this, that I'm going to highlight here in yellow, y equals a times b to the x power, is the format that my answer should be written. And the 2 data points that I'm given, 1, 6 and 3, 3, 54, those are x and y values that work when I plug it into my equation. So what I'm going to do in step 1, like it says here, we're going to substitute x and y into the equation. So I'm going to go ahead for both of my 2 data points. I'm going to substitute 1 for x, 6 for y, and then 3 for x, 54 for my y value, into y equals a times b to the x power. So what that'll look like, y equals a times b to the x power. So again, y is 6, x is 1, and then y equals a times b to the x power. So 6 equals a times b to the first, 54 equals a times b cubed. So from here, what I have to do is now solve that system for both a and b, and my suggestion is going to be using substitution. Now, the one that we substitute does make a difference in how easy it is to do the substitution. So if we notice here, both of my 2 equations have an a in common. Right? They're both just a to the first power. Nothing else funky happening to it, no exponents on it. It's just a. So if I solve one of my 2 equations for a, I can then substitute that into my other equation for a. That's what substitution looks like for a system. So if I go ahead and solve my top equation, which is 6 equals a times b to the first power, which is a times b, if I solve that for a, I would divide by b on both sides, and I get that a is 6 over b. If I now take that and substitute it in for a in my other equation, my bottom equation, which I'm going to switch to red for this, my new equation after I do that substitution would be 54 equals 6 over b times b cubed. And now I have a single equation that just has b involved. So I should be able to solve that one without much of an issue. So to be able to solve this, I'm going to make sure I get my b's combined. Here, this is technically b cubed over 1. So if I multiplied those together, I would have 54 on the left side, 6b cubed over b. And now I have to use those exponent rules that we reviewed at the beginning of this chapter to simplify this. This is b cubed over b to the first power, so I can cancel one of those out. Or if you want to use those exponent rules that I was just referencing, quotient rule. So that means our rearranged equation here, 54 equals 6b squared. So if I divide by 6 on both sides, I get that 9 equals b squared. So then we just take the square root of both sides, and I get that b is positive 3. So that's my first solution. I get that b is 3. I now have to go back to one of my original 2 equations to solve for a. So I'm going to go back to my top equation. My original top equation was 6 equals a times b. We now know that b is 3. So if I'm going to solve for a, I have to divide by 3 on both sides, and we get that a is positive 2. So I have now successfully identified both a and b. I have solved that system. I have everything that I need to move on to step 3. Step 3, which is super simple, is just putting those two values back into my equation. Because remember, my equation in general, the generic form of an exponential, is y equals a times b to the x power. So if I plug in 2 for a and 3 for b, that will give me my final answer. The equation that would give me those points would be y equals 2 times 3 to the x power. That would be my equation for number 3. We're going to try one more of those. We're just going to go through that whole process again for number 4, just because I know it's complex, it's complicated, it's a new process here. We're going to do some practice with it. So for box 4, same instructions. We're going to use y equals a times b to the x power to write the equation for the exponential that goes to the point. Now my coordinates are 1, 12 and 3, 36. So again, I'm going to go ahead and write my system. I will say, all right, well, y equals a times b to the x power, y equals a times b to the x power. So I just have 12 equals a times b to the first, and 36 equals a times b to the fourth. Once again, my a is always going to be the easiest one to solve. I would even solve it in your top one because it's super straightforward. If I rearrange that top equation, I should have a equals 12 over b, because all I have to do is divide by b on both sides. So if I now take this 12 over b and replace my a in the bottom equation with 12 over b, that'll give me an equation that I can now solve for b. So 36 equals 12 over b times b to the fourth. After I multiply those together, my b to the fourth and my b underneath is going to cancel and reduce that to b cubed. So 36 equals 12 b cubed. I divide by 12 on both sides. That gives me 3 equals b cubed. So now, to get my b by itself, we're going to have to take the cube root of 3. So you're definitely have to use a calculator for this one. And what we should end up with, if we do our cube root of 3, let's see, 3 to the 1/3 power. I get, if I round to 2 decimal places, no, let's do 3. Let's be more precise. 1.442 should be my b value. That is the cube root of 3. So not the prettiest thing, but once again, we've got our first solution. I can now take this b value and plug that back into my other equation to solve for a. So if a is 12 divided by 1.442, I'm going to go ahead and just, again, grab my calculator. 12 divided by 1.442. We should end up with an a value of 8.322. So putting those together, my final answer should be a equals 8.322 times 1.442 to the x power. Not the prettiest of equations, but for as ugly as it's going to get for us, that wasn't so bad. Once you get the hang of it, the process itself is very similar every single time, so the more practice you do, the easier it will get, as always. So, homework is on the screen there. It is on page 346, number 4 through 20, just the evens. And as always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. See you soon.